All right, so what is this? Yeah, it's a diagram of an atom. It's kind of a model. You know, over the past 150 years or so, what scientists have thought an atom looks like has changed quite a bit. Okay, it's gone through different stages that we may talk about as we move on through this unit. And so there's different ways to think about it. This is one way where you have a central part of an atom and then some of the other subatomic particles sort of flying around the outside of it. And we'll talk about what those things mean in a few minutes. Well, let's start with just some basic definitions. These are probably some words you can define. An atom. So what is an atom? See?
Basic unit?
It is the basic unit of all matter.
They make up everything?
Makes up all matter, yeah. An atom is also, though, itself made up of even smaller pieces. Atoms are actually made of some different, what we call subatomic particles. And the three we're going to be concerned about are protons, neutrons, and electrons. You guys heard of those things?
Yeah. Yes.
Okay. So do you know what they are, where they're located in an atom?
Little.
Where'd you learn about them? Elementary school?
Well,
Yeah. All right. So we have atoms, the building blocks of matter. Elements are pure substances that are just made of one type of atom. Like gold. What is gold made out of? Just gold. It's just gold atoms. It's not made of any other stuff. It's pure. And the periodic table is technically called the periodic table of elements. The periodic table that I just gave you lists all of the known elements on Earth. So an element is a pure substance. But then elements can combine with each other. And they form compounds. When two or more elements bond together to form something, that's called a compound. For example, carbon dioxide, CO2, is a compound. It's made of carbon atoms and oxygen atoms. Two elements bonded together. And then the smallest part of a compound is called a molecule. So a single molecule of carbon dioxide is the smallest amount of carbon dioxide you can have. So if we put some of these words into use here. Hydrogen and oxygen are, how will I fill that in, Sophie? Or what? No. Hydrogen and oxygen, they're not compounds, Rosemary. They're elements. They're just pure substances. Things on the periodic table. Oh. So, when two blank of hydrogen, two atoms of hydrogen and one atom of oxygen combine, they form one blank of the blank water. Nicholas, one? No? Matt?
Molecule?
Molecule of the, Nicholas? Compound water. All right. So if we take a single atom and look at what it's actually made of, we get into what we call the subatomic particles, smaller than an atom particles. And for our purposes, there's 3 subatomic particles, because really those are made of other subatomic particles. It's very, very complex. We talk about the physics of the atom. But for our purposes, we're just talking about protons, neutrons, and electrons. So there are 3 subatomic particles. And an atom itself is made up of a central part, which you see here and here, that's very, very dense. Okay? And then there's a larger area around it where you have other particles sort of flying around. So the first subatomic particle is the proton. It's found in the nucleus. And these subatomic particles have an electrical charge to them as well. Do you know what charge a proton has? Brandon?
Positive.
Yeah, it has a positive charge. The other subatomic particle that's found in the nucleus are neutrons. Anyone guess what charge a neutron has? The name may tell you. Sarah? No, that's what everyone always wants to say. Brandon? Yes, it has no charge. It's called a neutron because its charge is neutral. Okay, it's neutral. It doesn't have a positive or a negative charge. It's just neutral. So those are the 2 subatomic particles in the nucleus, all packed together very tightly, protons and neutrons. Then there's the other subatomic particle, the electron, which is orbiting around the nucleus in a way. An electron, Habib,
Negative charge.
has a negative charge. All right, so here we have the nucleus of an atom, protons and neutrons, with the electrons around the outside. Here again, this is a hydrogen atom. We have a proton, we have a neutron, and then an electron flying around the outside.
How does the nucleus stay like in midair?
It just is. It's just sort of, it's just there in a sort of little, and it's so small that, that sort of different laws of physics apply to it. Quantum physics applies to electrons and small particles.
And you can see it.
They haven't seen it.
And how do you know it's like that?
So how do they know it's like that? Through experiments. Through experiments. And we may get to this activity where several scientists have done different experiments where basically they send particles flying at atoms of a certain substance. And one of the experiments they found is that most of the particles they sent flying at them, even though they had a solid sheet of gold, a very thin layer of gold, when they sent these particles, it would just pass right through it. That helped them to start to understand that most of an atom is actually empty space. But once in a while, one of these particles that's going into the gold foil would bounce off at a strange angle, because that's one that hit the nucleus. So they use this information to sort of start to think about how big the nucleus is, how much of an atom is empty space. And we actually have an activity to do where we recreate that using like marbles instead of particles.
Like when they're doing that experiment, what happened if one of the particles hit the rings?
At what rings?
Like the
These
ring?
electrons?
Yeah.
Basically, they are so small that almost never happens. Okay? We'll talk about that experiment. It's called Rutherford's gold foil experiment. All right, so we'll come back. I want to show you that video in a couple of minutes, but we'll save it towards the end. So you have this periodic table. Have it out or open so you can see it as we're talking in the next couple of slides, because it's going to be important. You'll need this with you all the time. We'll be referring back to a constant. So what do you know about the period? Does anybody know anything about the periodic table or what it is or any information about it? Abid?
I think there's families and groups.
Okay, there are families and groups. We'll talk about that. Brandon? Yeah, it's organized in a certain way by increasing atomic number.
They're also separated into metals and non-metals.
Okay, that some parts of the periodic table are metals and other parts are non-metals. Yep.
The ones closer, like, to the bottom are, like, the one that little space, like, where there's,
Here?
yeah,
Oh, these? Okay, yep. Good. All right.
Some elements can be put together.
Okay, some elements can be put together. So,
There's like a line that separates the elements from the building.
oh, there's a group called the noble gases. Yep. Yeah.
There's sodium and water exposed.
Okay. Good. All right. So yeah, so you guys know some of you know a fair amount about the periodic table, and all those things you guys were just telling me are all correct. So the periodic table of elements lists all the known elements that we have, that we know, including some man-made ones that are only around for milliseconds, but we're not going to be very concerned with those. And these include some things that are familiar with you, you know, aluminum, lead, gold, oxygen, nitrogen, as well as some things that you probably are not familiar with, Einsteinium, Americanium, Durosium. Those elements are probably not as familiar to you. But we'll talk about and we'll learn about some of them. You do not need to memorize the periodic table. You'll have it available on your quizzes so that you do have to know how to use it. But this periodic table, it's sort of a strange shape. It's got all sorts of numbers on it. And they all are there for a reason. Okay? The periodic table, the way we have it today, was first sort of organized by a man named Dmitry Mendeleev, a Russian scientist. He did his work in the middle of the 1800s. And he sort of placed the elements in certain parts of the periodic table in an organized way that helped him predict their properties. In fact, Mendeleev, when he made the periodic table, they didn't know about certain elements yet. He knew, but when he organized it, he left some blanks. He said, well, someday we're going to find an element, and it's going to have these properties, and it's going to combine with other elements in this way. Okay? And later on, we did find those elements to fill in those blanks. So it's a pretty smart way to do this. And so the periodic table lists all the elements, and the periodic table goes from left to right, increasing in atomic number. So if you actually look at your periodic table, if you start in the top left with hydrogen, its atomic number is 1. If you go across the periodic table to helium, that's number 2. Lithium is 3. Okay, beryllium 4. Then go across. Okay, then we have boron, carbon, nitrogen, oxygen, fluorine, neon. And so as we go across, the atomic number increases. Okay? And it continues all throughout the periodic table. Now, the rows of the periodic table, okay, we call them periods. And everything in one row has the same number of electron shells, which we'll talk about. But what's very important are the columns. The columns up and down, we call them groups or families. And elements that are in the same group behave in a similar way. They have similar properties. Okay? So hydrogen, lithium, sodium, potassium, all of those elements, they all behave in some similar ways because they're all in one group. And there's a reason for that. It has to do with the number of electrons in the outermost shell. Each element also has a symbol. Okay, and you see that some of the symbols are a single capital letter, like hydrogen, capital H. Some are 2 letters, a capital and a lowercase, like helium. Now those seem to make sense, hydrogen, helium, H, He, but many of them may not seem to make sense. Like gold. What is gold? AU. Lead. PB. Okay. Potassium is K. Sodium is Na. So there are many that don't seem, they're not necessarily named after the English names of these elements. Where do you think many of them come from? Okay. Leah? Yeah, many of them come from Latin. Some come from Greek. Because these elements were actually named long ago. People have known about gold, for example, for a long time, and lead. And so the symbols are sort of a holdover from those names in other languages. All right. So let's talk about what some of these numbers mean in the periodic table. And different periodic tables, the one you have in your agenda may look different from one online, which looks a little bit different from the one I've given you. The numbers can be in different spots, but you need to recognize what they all mean. So first off, atomic number. We already mentioned it. It's a whole number. It's generally the biggest number for each element on the periodic table. And the atomic number tells us how many protons there are in the nucleus of one of these atoms. So a carbon atom has 6 protons in its nucleus. This is what determines that it's carbon, the number of protons. No 2 elements have the same number of protons. So carbon is the only element that has 6 protons in its nucleus. If it had less, it would be something else. What did we say about protons and their charge? Okay. Matt? It's positive. But overall, every atom is neutral. Electrically, it's neutral. So if it has 6 protons, what must that also mean? Nicholas?
It has 6 electrons.
That it also has 6 electrons. So the atomic number also tells you how many electrons that atom has. So carbon has 6 protons in the nucleus and 6 electrons flying around the outside of the nucleus. Okay, then we have another number, the atomic mass. It's a decimal. It's actually an average. And this is called the atomic mass. It tells us basically how much mass the nucleus of that atom has. So if you look at the atomic number and sort of round it, it tells you the total number of protons and neutrons in that atom. So if we look at carbon, carbon has 6 protons, we just said that. How many neutrons does it have? Yeah, it has 6. 12 minus the 6 protons, and there must be 6 neutrons. So it basically gives you the mass of the atom. And when we're measuring the mass of atoms, they're very, very small. These are tiny, tiny little things. So we can't use grams. We can't use even milligrams. Okay? Scientists actually had to invent a new unit to talk about the mass of an atom. And the units that we have for mass are called atomic mass units. AMU is the symbol. And it's very simple. In this system, a proton has a mass of 1 AMU. A neutron has a mass of 1 AMU. An electron is so very small that we basically ignore its mass and say it has a mass of 0. Technically it does have some mass, but it's like if you stepped on the scale and weighed yourself, then you took a little piece of lint out of your pocket, what would the scale say? It's the same thing. Does it mean the lint doesn't have mass? No, it's just too small to really measure or to have any consequence.